As an analyst, I cover mobile infrastructure typically deployed by service providers. Infrastructure involving LTE, HSPA, even Wi-Fi. Been doing this for many years. But in addition, I'm also an emergency services worker. For many years, I volunteered with the Montgomery County Fire and Rescue Service in Montgomery County, Maryland. On a regular basis, I'm responding to fire and rescue emergencies and utilizing the communication systems that we have in service today. It's a unique perspective. I have views into the evolution of the technology as well as use cases and operational environments that are specific to public safety. Well, today we're going to be addressing the subject of public safety operations and in-building coverage. Public safety operations are very difficult, clearly. Law enforcement, the fire service, emergency medical services, these operations become very difficult in large, complex structures. Our discussion today centers around the evolution of in-building coverage systems, why they matter, what is changing, what are the challenges with these systems, and how do we serve the community today and ensure evolving needs are met, all within budget. Radio operations are central in today's emergency services operations. From dispatch to execution of the mission, what was once a voice-only capability is rapidly expanding to voice and data. Radios have limitations, and these limitations can impact operational effectiveness. In the early days of voice communications, traffic was broadcast in a very analog fashion. You push the button on your handset, your microphone, your transmission was immediately received by all listeners. In the old days, radio frequencies were quite low. My first radios were at 154 megahertz for transmit and receive. In the United States, many state police agencies in rural areas continue to operate at 33 megahertz. With these low frequencies, when I think back, I cannot think of many situations where I failed to reach outside of a building that I was operating in. Things have changed. Most voice communications today take place on systems that are operating at 400 megahertz or higher, frequently on trunk systems. And in these trunk systems, the handset communicates on an uplink to a tower receiver that then forwards a signal to a central controller. If this controller is not reached, no communications via the trunk system are possible, and people who are working on an incident have to switch to a talk-around mode, which eliminates many of the features of the trunk system, unfortunately. Around the globe, most trunk systems are Tetra. It's a standard created by the European community, typically operating in that 400 megahertz range, but with very narrow bandwidth and very limited data capabilities. In the United States, Canada, Australia, New Zealand, we have APCO Project 25 trunk systems in place. For many of these, particularly in the United States, we're now operating at 800 megahertz, so much closer to the cellular frequencies. And in addition, we're getting some new frequencies at 700. Like Tetra, the bandwidth is very narrow. Data communication capabilities are a bit limited. Trying to advance the slide. Thank you. When public safety network operations move to higher spectrum bands, some challenging problems occur. Propagation characteristics have an impact on radio system performance. More base stations are needed. The higher the frequency, the more difficult it is for the RF wavelengths to penetrate buildings or extend over the landscape. Indoor spaces become resistant to high-spectrum RF, leaving large areas of heavily populated structures without access to emergency services, repeaters, outside. Operationally, this means loss of connectivity to the trunk system, pushing people to direct unit-to-unit communications, and eliminating functions such as the emergency button. And it creates a requirement that there be vehicle-borne repeaters brought to the scene of incidents, hopefully in time. And even those repeaters may not be successful if the units are operating too deep in a structure. So these complex environments bring some unique challenges. And to be sure, not every in-building deployment is the same. Complex environments such as transit systems, airports, large government facilities have unique requirements. The characteristics of these environments are different because they, from a threat level, provide very attractive high visibility targets for attack. They involve operations that potentially encompass thousands of civilians in the vicinity. Frequently, these areas involve hazardous materials, large equipment, moving vehicles, and even flying aircraft. When things go wrong in these environments, incident command depends on robust data to understand the environment and the operations. Operational areas can cover sprawling building complexes. Think of your normal airport. These are environments with very challenging indoor and subterranean levels. Frequently, these environments have dedicated on-site public safety units. Most airports have fire departments, as well as law enforcement agencies on-site, part of staff. The full range of operational communications at these facilities are needed 24/7 for both voice and data. So what are the consequences of not providing good communications? Well, sometimes those consequences can have a deadly result. In January in Washington, D.C., near where I am, we had a relatively minor fire in an electrical component in a subway line. Unfortunately, the tunnel distributed antenna system was not working properly. And systemic issues with this tunnel coverage stripped the firefighters of essential situational awareness during the event. The result was catastrophic, even though the property damage was minimal. These complex environments require special attention for the safety of the public and for the safety of the emergency services worker that must mitigate problems. Not only everyday problems, such as a heart attack, sick person on a subway platform or in an airport concourse, but once-in-a-lifetime problems that may arise. Well, into this demanding environment comes some change. The urban landscape is evolving with larger, more densely occupied structures. Old approaches for radio coverage that rely on centralized radio transceivers, or in the case of our cell phone systems, antennas slapped to the side of buildings, start experiencing coverage limitations. One particularly impactful change is the material used to clad buildings. Low emissivity glass offers significant benefits to building owners seeking lower energy costs. Unfortunately, the material is also excellent at preventing RF energy from entering or exiting the structure. Recognizing this issue, in the U.S., the National Fire Protection Association incorporated text for in-building public safety radio enhancement systems into the country's 2009 Model Fire Code revision. Matching text is also now in the ICC International Fire Code. Adoption of the model text varies across the United States, but some jurisdictions have embraced the concept as part of the local fire code. My own jurisdiction in Montgomery County, Maryland is an early adopter, and we are starting to see benefits from the provision. It is difficult to overstate the importance of these changes. Here, for example, is the map of an apartment building in my first due area. The layout of the structure is complex, with many stairwells and sublevels containing mixed commercial and retail occupancies. We have had multiple significant fire operations here, including a fatal fire. Communications with vehicle repeater systems are less than ideal. Clear, consistent voice communications between incident command, division supervisors, crews operating on the fire floor, and crews operating in other portions of the structure are vital. In-building systems, or what the NFPA terms as radio enhancement systems, can make the difference between safe operations and disaster. Note that this structure, as complex as it is, pales when compared to sprawling occupancies, such as airports, stadiums, and government facilities. The Pentagon is a perfect example. Not only are occupancies changing, however, the radio systems are also changing. We talked about the arrival of trunk systems around the world, but more radical changes are in store as LTE becomes available for public safety operations. The U.S. has embarked on a national public safety broadband network with creation of FirstNet. Initial FirstNet deployments focus on augmenting mission-critical voice communications with data applications supported on LTE. To be sure, agencies in the U.S. use data applications today in advance of FirstNet. Mobile data terminals and vehicles typically use mobile network operator LTE services to send dispatch information. But FirstNet creates the prospect of much richer application functionality moving into the hands of the incident commander, law enforcement officers, and other emergency services workers. As video becomes operational, the radio system requirements at large facilities, such as airports and government complexes, will need to handle the new frequencies and radio carriers. Simply supporting an air interface that works with vehicles on easy-to-cover roadways will not cut it. The U.S. is not the only nation moving in this direction. The United Kingdom is looking to LTE as an alternative to an expensive national TETRA system. If the UK succeeds, it will serve as the proving ground for taking LTE far beyond public safety data applications, to eliminate the costly private TETRA system with a system based on mobile network operator LTE. The full set of 3GPP Release 12 and Release 13 enhancements will be implemented. This means priority and preemption. This means LTE Direct. Ultimately, the rest of the world will move in this direction, and a new form of public safety communications will take root. Beyond the US and UK, Korea as well is aggressively moving in this direction. In fact, Korea may be the first country to deploy a dedicated LTE network for emergency services. We are already seeing indications that the LTE system suppliers are moving to support the Korean requirements. So that's a quick run through some of the issues surrounding public safety radio enhancement. This is a critical but typically hidden problem. It's important that we surface the issue and help our society move forward towards a solution. So, thank you.
Thank you, Ken. So before I pass the mic back to Lance, we'd like to gather everyone's feedback, our view on LTE with 2 polls. So we'll just leave it here for a couple seconds. The question is, do you have plans to migrate to LTE-based public safety system? And the choices are yes, no, and not sure. So I see there's some people clicking, so we'll just give it a few more seconds. And then at the end, I'll share the results at the end of the webinar. Okay. All right, so on to the second question. When do you plan to implement an in-building public safety solution? The choices are within the next 12 months, 2 to 4 years, 5 to 7 years, or not sure. So the results are still coming in. So we'll just give it 10 more seconds, and then I'll pass the mic to Lance. All right. So right now, I'll pass the mic over to Lance.
Thank you, Wendy. Thank you, Ken. As Wendy has already mentioned, my name is Lance Kraft. I'm the Vice President here at Dali Wireless. My role and responsibilities on a day-to-day basis are for the sales and sales operational functions in the Americas region. In the next few slides, we'll discuss who Dali Wireless is, what Dali Wireless does, where we are, and how Dali Wireless products and services satisfy the public safety requirements today and into the future. Dali Wireless was founded in 2006. We are headquartered in Silicon Valley, US. And for those of you who are familiar with the US market, we're actually based in Menlo Park, California. Our research and development team is located in Vancouver, Canada, and we have global sales and customer service teams located throughout the Americas, Europe, and the APAC regions of the world. Dali Wireless has designed, developed, patented, an award-winning all-digital DAS system for commercial and public safety bands. We have over 200 patents globally, supporting America, APAC, and EMEA public safety frequency bands. So as we look at the public safety requirements today, we have to recognize that there are many things changing. Things such as government and municipalities are passing ordinances requiring in-buildings public safety coverage. It still doesn't remove the question who's going to pay for these systems. We also recognize an increased requirement for mission-critical communications to be protected at all times. And we'll talk about this further on in the presentation when Sasha is presenting. Techniques in the design known as fault tolerance and fully redundant systems. We're also seeing police, fire, and rescue, all local services with multiple channels residing on a single system. So as we go through the presentation, you'll see we support P25, Phase 1, Phase 2, LTE, and even the Tetra bands in Europe and APAC. So what are the future requirements of public safety? The growing trends of high-speed data are obviously requiring the migration from narrowband to broadband. It's also going to require the LTE support for the broadband services and the video transmission requirements of public safety. And as Ken mentioned, a national interoperability system known here in the U.S. as FirstNet is well underway and plans proceeding accordingly. So what are our options? When you look at the options available to us, voting receivers are used with older channelized systems to equalize talk out and talk back. We believe you'll still see repeaters used in small buildings, feeding a passive distribution system. Dali, as we mentioned, we do a digital DAS. We obviously believe digital is better. It offers lower noise floor, no loss in fiber infrastructure, the flexibility of packet data distribution with a higher throughput. So with these options, we believe at the end of the day, public safety means reliable coverage and access at all times. It means coverage in all public areas, including stairways and harsh underground environments. As a result, a public safety system should be able to cover all public safety areas. It should satisfy current and future requirements for ease of expansion, for upgrading to LTE, for broadband communication. At the same time, consideration for fault tolerance and redundant design. And all digital DAS, as Dali offers, can satisfy these requirements. I will now pass the mic back to Wendy.
Thank you, Lance. Now that we've heard from both Ken and Lance about the current and future requirements of public safety, Sasha will now go over how we can satisfy these requirements in more details. But before we do that, there will be a third poll. And this topic is your local government requiring new buildings to have public safety system installed? Same as before, we'll share the results at the end of the webinar. We'll just give it a couple more seconds because votes are still coming in. Okay, now I'll pass the mic on to Sasha.
Thank you, Wendy. So my name is Sasha Trajkovic, and I'm a VP of Engineering at Dali Wireless. Greetings to the audience, and thank you for participating. We'll start, and in the next few slides, we'll try to touch upon requirements of the public safety distribution systems for scalability, availability of service, and also security. So, Wendy, can you please give me the keyboard control? Thank you. So let's start with public safety interdistribution systems need to satisfy current and future requirements for expansion or to upgrade to a new bands, new standards, or waveforms. So before I start with that, let me try to provide a brief description of a modern digital distribution system. So the system is comprised of a couple of key elements. The host unit receives the RF content from a source, which can be a dedicated base station, or the signal can be tapped from the macro tower that provides outdoor coverage. So that RF content inside the host unit is translated to a digital data stream. And then over the fiber optic network, using star topology or star daisy chain topology, that content is delivered to the remote units, which are strategically located at the particular areas of the venue that requires coverage. Remote unit translates the data stream received into the RF signal, and via antennas, single or multiple antennas, it's broadcasting that content to the users. So the first question we have is, or first requirements, is ability to aggregate content if the base stations or off-air repeaters are not co-located. This is specifically true for the venues which are dispersed over the large area, like airports or railways or subway systems. So this requirement can be, in essence, achieved by connecting additional hosts at location number 2, where the resource exists for additional band, and then daisy chaining that host to the primary host. On this way, the content is aggregated at the primary host, and data exchange is done at the level of baseband, at the level of a data stream. Another requirement which we usually see in previously described venues is ability to transport multi-channel and a multi-band content from head-end location, so here, to remote locations over a single fiber optic link. This can be due to the fact that some of the venues have very limited fiber infrastructure, and some of the distances which are required are quite large, quite long. So digital distribution system has ability to transport content up to or more than 20 kilometers in range. Also, the data rates which are currently used on a fiber optic link are up to 10 gigabits per second, which translates with a quite large content. And in this particular case, specifically for enterprise environments, cellular and public safety content can be aggregated and delivered to the remote units if that venue requires such application. Another requirement is its easy addition of the new channels and bands. So this can be done on a couple of ways. If the particular band that if there is anticipation that particular band will be added in the future, that band can be actually integrated into a system prior to installation, and then when time comes can be simply enabled. In the case of modular systems, the new band can be simply added by plugging RF-specific modules at the host or at the remote. Obviously, this is possible only if the modular system has available expansion slots. If those two cases are not applicable, the solution is, again, to introduce additional host, which will process additional band or bands, and then aggregate that content with existing infrastructure. On the remote side, similarly, additional remote will be daisy-chained to the existing remote and RF output summed and delivered to the antenna. This requires very limited change to the infrastructure, meaning just the work inside the central office and at the location where the remotes are installed. On the other hand, the fiber infrastructure, the coaxial infrastructure towards antennas is untouched. Finally, you may have a requirement for easy upgrade to a new standards and waveforms. What is important to mention here is that the modern digital distribution systems are software-defined platforms where the digital signal processing is conducted inside field programmable gate array devices, or FPGAs. So implementation of the future waveforms that may require different type of digital signal processing can be achieved by remotely programming these devices to implement new signal processing algorithms, and in that way satisfying needs for those new waveforms. Just to be clear, LTE is not a new waveform. It's existing waveform. So for current public safety bands, they shall be LTE ready. One example of that is that Dali's 700 public safety bands are FCC certified, not just for P25 waveforms, but also for LTE operation that is in anticipation of the FirstNet service becoming available. Switching to the next slide. So besides quality of service, the availability of service is extremely important in a mission-critical communication systems. The system cannot suffer loss of service due to a single point of failure. The requirement for a public safety grade communication network is 99.999%, or 5 nines of availability. This corresponds to downtime per year of around 5 minutes. To be able to achieve something like that, a certain level of redundancy needs to be added to a system. So let's again go over this simple structure here. So we have a source that is of a repeater or base station. The RF content is delivered to a host, and then via fiber optic link, that content is delivered to remote unit receives that content, translates back to RF, and radiates using antennas. So what is important to mention here is following. If we assume that coverage design on antenna side is done with a high level of overlap between antennas corresponding to different remotes, that means that we have a certain level of spatial redundancy here. Then the host unit becomes a single point of failure. To address this, we can introduce a fault-tolerant system where we have a secondary host that operates at or in 1+1 redundancy, meaning that is on a hot standby and moves in an active mode if a primary optical link is cut or primary host is in failure. So again, if primary host fails, or we have issue with the primary optical link, the remote unit will automatically sense the fact that the data are not coming on a primary optical link and will automatically switch to a secondary optical link. What is important to mention here is that the secondary optical link needs to be routed using a different path than the primary optical link. That will actually provide one-to-one fiber link redundancy. Another important point is that due to this change, the delay to particular remote will change. Modern distribution system, digital distribution systems automatically measure the delay, and they do automatic adjustment. So all the remotes are broadcasting in the same time. To further increase the resilience of the system, we can add redundancy on a source side, meaning that we can introduce a secondary base station or a repeater, and on that way, if the primary repeater fails or primary base station fails, it will automatically switch or bypass the functions to the secondary repeater. We can also increase redundancy on a remote side by introducing a secondary remote. Primary remote has an optical bypass switch, integrated optical bypass switch, and integrated RF switch. So in the case of the primary remote failure, the optical bypass switch will switch to default mode, which is bypass, and the optical or data, optical signals which carry data, will be delivered to a secondary remote. Secondary remote will do its function, amplify, convert the signal to RF, amplify that signal, and over the RF bypass switch, deliver the signal to antennas. We can go to extent of actually also providing secondary antennas, or on a source side, providing also secondary directive antennas, directional antennas pointing to different towers, and in that way achieving some level of spatial source diversity. So this will be an example of a fully redundant distribution system. Moving to the next slide. Another important requirement for public safety distribution systems is to provide security, provide secure bidirectional communication, which protects against spying or eavesdropping, against tampering with the content, or forging the content of the communication. Current handsets are providing encryption. So beside that layer of encryption, digital distribution systems are adding additional scrambling of the payload data, which increases protection of the content if the content is intercepted during transport. So if somebody taps to a fiber link and gets the data stream, it will not be able to reconstruct the actual information simply because we have two layers of scrambling. Another important point is access to the distribution system. Distribution system has a control and monitoring functionality, and the user, authorized user, is accessing that functionality by simply browsing into a web server which is inside the host unit. To provide proper protection, this access is password protected and encrypted. So for encryption, for protection, HTTPS or HTTPS secure protocol is used. That provides authentication and also bidirectional encryption of the communication between the user and the web server. So these were the possible examples of requirements that contemporary distribution systems face and how those requirements can be satisfied. Wendy, back to you.
Thank you, Sasha. That was very informative. We'll do our final poll question before I pass it back to Lance. So this question is, how likely will you implement a fault-tolerant or redundant system if available? So as previously mentioned, we'll share the results towards the end of the webinar. So just give it a couple more seconds as the folding is still coming in. Okay, so I'll pass the mic back to Lance.
Okay, thank you, Wendy. As it relates to the Dali differentiators, obviously we are all digital. And as Sasha described, we also are end-to-end digital RF signal processing. We also believe a simplified architecture as a result of being able to re-image our FPGAs as new modulations are introduced in the environment of wireless. We also, as you heard, IP pass-through, content IP pass-through, flexible topology, offering a unique design, as you heard, with fault tolerance and even redundancy. We are software configurable. This allows us a lot of flexibility and scalability, as well as Sasha talked about the additional data scrambling and encryption that's offered through our digital architecture. We also, from an agile digital filtering, I believe this is a significant differentiator of the Dali solution as it relates to public safety. So again, we're programmable, agile, elastic, secure, and very cost effective. Very competitive as it comes to designing and offering pricing. As we have seen competitively in the marketplace, we are very price competitive. Our product lines include the T-Series, as we mentioned, the T30, 30 dBm or 1 watt, T37, our 5 watt, and T43, our 20 watt. We also have released our new Dali Matrix, which offers additional broadband capabilities across the fiber, as Sasha mentioned, and more modularity than what we have in the T-Series today. However, both systems, when we do a design, we would select which system makes most sense for your solution. Narrowband LTE is used for public safety communications today. As the industry migrates to a broadband LTE solution, obviously there's going to be a lot more advanced features, including real-time incident monitoring, health monitoring, and other applications that require the broadband nature of LTE. We absolutely believe this is going to happen, but as these things become available, as the industry migrates to broadband LTE, the public safety agencies will ultimately decide how the LTE will be used for their solutions. We also want to point out We also want to point out, in an enterprise, for those of you who may be a building owner or enterprise owner, and we mentioned how the government and municipalities are requiring in-building services, especially for new buildings being built. We can design these systems. In the U.S., we typically see almost a 90% or higher, maybe even 99% or higher, where the systems must remain separate. However, throughout the world, we are seeing requests where they want these systems integrated. So we have the design architectures and the capabilities to integrate these systems across a single fiber, sharing a single remote, or offering at the edge different remotes for each of the services. However, as you can see in this design, what we want to point out is that we can design it as separate systems, and we can also, because of our unique platform, integrate the systems together. For our final slide, questions still remain. Relating back to what the questions are, as it relates to public safety, who's going to pay for the systems? If they're required, that's good opportunities for companies like Dali. However, who's going to pay for these systems? Who's going to maintain these systems? And we obviously know not all the answers are answered yet, or all the questions are not answered yet, but as far as an integrated solution that allows fire, EMS, and police to operate on a single communication network. And then there's obviously the E911 question. How do we solve the E911 questions as well? So with that, Wendy, I'll send it back to you. Participants, we thank you.
Thank you, Lance.
Yes,
thank you, Lance. Before we go into the Q&A, let's look at the results of the poll. So we have 4 questions during the poll. So the first question that we had was related to LTE. Do you have plans to migrate to LTE-based public safety system? Majority were yes. And the second question was, when do you plan to implement an in-building public safety solution? And it seems like the popular choice was the within the next 12 months, followed by it's actually within, not sure, and then followed by within the next 12 months. And then, is your local government requiring new buildings to have public safety system installed? The majority of the answer is yes, which was what Lance and Ken alluded to earlier as well. And the last question is, how likely will you implement a fault-tolerant or redundant system if available? And the majority of the answers was yes, followed by, was not sure, followed by yes. So with that, I want to thank you again for everyone's feedback on this poll. Now we'll go into Q&A. We have received quite a number of questions, so we'll try to answer all of them within the next 10 minutes because I know we're running a little bit late already. So for any of the unanswered questions, we'll reach out privately with an answer afterwards. So the first question is, probably this one is directed to Ken. Can you please explain the priority exemption on LTE, please? Here in the UK emergency services, we have not moved over to LTE based.
Yeah, so the UK is preparing to move. They certainly have not moved over yet. The Home Office has plans for and contracts that are being in the process of being let that will rely upon LTE as the transport. Now, 3GPP, which is the standards organization governing how the protocols work, has provided work items that will expand upon priority and preemption. The mechanisms should allow a network, and I believe the main operator in the UK that's bidding right now is EE, to successfully deliver high-quality, mission-critical communications, even when their own customers, who are consumer customers, are in a cell sector. The mechanisms will be put in place by the manufacturers of the systems, Ericsson, Huawei, Nokia, to ensure that a police officer that is depressing their push-to-talk button gets preference over the other users. But as the question indicates, the UK does not yet have this network operational.
Okay, thank you, Ken. The second question is, do we need to make any hardware changes when we upgrade to LTE-based system? Sasha, I think that's more for you.
Yeah, as I mentioned initially, in essence, current bands, since the LTE is in use for a while, current bands should be fully compliant to LTE. So, for example, if the current infrastructure has recently installed 700 megahertz band, that particular band should be LTE ready, or at least in a case of Dali, that's true. I mentioned that we are actually FCC certified for that. So the answer is no. There is no requirement for any hardware changes if that band is already in a system. If that band is not installed, like let's say the particular venue has only 450, 800 megahertz band installed, FirstNet comes in with 700 megahertz LTE requirement. Well, system needs to be augmented with additional hardware which will support the 700 megahertz band. In that case, simple daisy chaining of the hardware on a head end and the remote side should satisfy the need for integration of that band.
Okay, thank you, Sasha. And the next question is, can the system handle a mix of indoor and outdoor coverage? Lance?
Thank you, Wendy. The design architecture is with Dali is such that, yes, we can integrate indoor and outdoor design techniques to run off a single host. So if there is an area that requires in-building, but also there is areas outside, we certainly can do a design that would provide the necessary coverage, whether it be commercial or public safety, for indoor and outdoor off the same architecture.
Okay, thank you, Lance. So I think we have a couple more minutes, so we'll answer the next couple of questions. Next one is, can the same system handle different base stations of P25 Tetra and LTE-based public safety signals simultaneously? Sasha?
Yes. The point is that the bands which are installed, or the hardware that is installed, at least in the case of a Dali installation, is waveform agnostic, meaning that different waveforms can go through the system and be properly processed and on the other end broadcasted to the user. There are different requirements for linearity, specifically between a Tetra and P25 and LTE. Tetra has a higher requirements for linearity and intermod level at 70 dBc. So in this particular case, that band, if it needs to be a Tetra compliant, so requires a slightly more linear amplifier. Dali supports that because has in our portfolio Tetra bands supports that. So if Tetra band is installed, the same band can actually satisfy also LTE and P25.
Thank you, Sasha. So I think we'll answer one more question. Next question is, if I install my DAS system today, can I later add public safety? Lance?
The short answer is yes. There again, depending on what DAS infrastructure has been installed and what frequency we're looking at to install public safety or to light up the DAS with public safety would require what needs to be done, whether it's hardware or just work to add the RF infrastructure at the head end. So the answer is yes.
Okay, thank you, Lance. So I think that's all the time we have today. And again, sorry for the delay and the sound earlier today. But we're very honored to have Ken join us today during this webinar. And thank you, Ken, Lance, and Sasha for a very informative session. Just as a reminder, if you want to see the webinar again, or you can send a recording to your colleague. I'll send you the link in an email later this week. And also the DFW airport case study that was featured in Mission Critical, we'll send that along as well. Again, thank you again for joining us today, and sorry about the hiccup earlier. Thank you.